Hi student, welcome to chemistry class with Emerald, and in today's class we are going to be looking at chemical bonding and intermolecular forces. In this video today we are going to be looking at hydrogen bond, the importance of hydrogen bond in physical phenomena, van der Waals forces and its importance as well, and then we are going to be comparing the boiling and melting points of halogens, noble gases and alkanes as related to the van der Waals forces in them. This video is brought to you by Igota Virtual Learning. Let's look at hydrogen bonding. Hydrogen bonding is usually created or formed when hydrogen is bonded to highly electronegative atom, such as nitrogen, oxygen, and fluorine. The bonding electron pair during this interaction is drawn towards the electronegative atom, like what we have seen in the picture that is below. And of course, we know that hydrogen has no inner shell electron. And then, of course, in terms of atomic size, it is very small in size. So, therefore, the positive charge density that will be developed will be very high. So the nucleus of hydrogen atom is exposed to attraction by a nearby electron cloud, especially a lone pair of electron that is on the electronegative atom, like you have seen in that picture as well. So therefore, we can say that hydrogen bonding is the electrostatic attraction between hydrogen and strongly electronegative atoms, and of course and the lone pair of electrons on this electronegative atom. So the electrostatic attraction that is created when hydrogen is bonded to electronegative atom, and of course and the lone pair of electrons on the electronegative atom, you can see um, on the picture there how these bonds are formed from fluorine to hydrogen. Then an interaction, electrostatic interaction is created that leads to the hydrogen bonding. Okay, so we must look at key requirements for the formation of hydrogen bonding. We must look at key interaction of now. One of the requirements is that the hydrogen must be directly bonded to that electronegative atom. It must be directly bonded. Then secondly is that there must be lone pair of electron on the electronegative atom. Now before we go into this, let's take a deeper look again on this hydrogen bonding. Now note that uh, highly electronegative elements that we are talking about, they have a very strong affinity for electrons. So they usually attract the shared pair of electrons in the covalent bond toward themselves. And of course, this will result in the formation of a dipole, which leaves a partial positive charge on the hydrogen atom and a partial negative charge on the electronegative atom. So an electrostatic attraction between two dipole is set up like we have seen here, and when the positive pole of one molecule attracts the negative pole of another. So this attractive force is known as the hydrogen bond. Of course, hydrogen bond is weak, but it has important effect on physical properties of various compounds. An example is hydrogen fluoride and water. Later on, we'll begin to look at different importance of hydrogen bond like we have seen, but this is generally the explanation about how hydrogen bond is being formed. So we can look at various examples of compounds with hydrogen bonds. We talk about the hydrogen fluoride the other time. We talk about the alcohols, yes. We talk about the halides of group 5, group 6, and group 7. So when we talk about their halides now, um, we are talking about pH3, which is phosphine, NH3 ammonia. We talk about H2S hydrogen sulfide, H2O water, HCl hydrogen chloride, HF hydrogen fluoride, HI hydrogen iodide, HBr hydrogen bromide, and so on. These are examples of compounds with um, hydrogen bonding inside them. Okay, so let's look at another information that is very important. We usually have what is called the intermolecular hydrogen bond, which is an hydrogen bond that is formed between two molecules. And then we have the intramolecular hydrogen bond, which is hydrogen bond that is formed between two different atoms in the same molecule. Please take note of that. And then also note that the intermolecular hydrogen bond is stronger than van der Waals forces. Is stronger than van der Waals forces. Okay, so uh, let's take a quick picture at the inter and intra that we mentioned just now. In the intermolecular hydrogen bonding, you have an example is water, where you have the molecules of water at one end interacting with the molecules of water at the other end. So we have H to O, O to H, H to O, O to H, and the like. So this is intermolecular because they are interacting between two different molecules. But when we talk about intramolecular hydrogen bond, it occurs within the molecules of a particular compound. Uh, like an example is this orthonitrophenol that you see. The orthonitrophenol is still within that. The hydrogen bond is within that molecule um, that is there. So we have oxygen and hydrogen being directly interacting here. So there is an hydrogen bond that is created there. The same thing with this hydrobenzyide compound that is here. There is an interaction between oxygen and also hydrogen that is here. So an hydrogen bond is also created within that molecule as well. So this is a clear difference between them. But the one that is stronger in terms of strength is the intermolecular hydrogen bond. It is greater in terms of strength than van der Waals force. This is very important information. Okay, so let's look at some of the importance of hydrogen bonding in physical phenomena. For instance, number one is the anomalous properties of the hydrides, second period hydrides, especially hydrides of um, the group 5, group 6, and group 7. It is observed they have abnormally high boiling points um, um, when compared to their molecular weights. Of course, molecular weight is uh, key when we discuss boiling points. But in this case, these three have very low molecular weight. An example is water, which is 18. So they are not expected to have a high boiling points. Water, for instance, have 100 degrees Celsius. So what could be responsible for this? Now let's quickly find um, an explanation to this. Now you observe that in NH3, H2O, and fluorine, the key electronegative elements are N, O, and F, especially. That's NH3, H2O, and HF. The key electronegative elements there are N, O, and F. And then we notice that of course, they are highly electronegative atoms, so they are going to form predominantly intermolecular hydrogen bonds in their hydrides. Intermolecular, take note of that. And then we have said and established that intermolecular hydrogen bonds are stronger than van der Waals forces. So that means the energy that will be required to break this intermolecular hydrogen bond will be greater, and of course that makes them to have high boiling point. And of course, we have to look at the order of these boiling points in them. Hydrogen H2O rather is greater than HF and NH3. Why is this so? Because H2O can form two hydrogen bonds per molecule. H2O can form two hydrogen bonds per molecule. um, HO to HO. So you can form two hydrogen bonds per molecule. While NH3 and HF can only form one hydrogen bond per molecule. So therefore, the boiling point of water will be greater than those two. Then when we compare between N and F, F is more electronegative than N, and as a result of that, the intermolecular hydrogen bond between HF molecules will be stronger than that of NH3. So HF, again, we have higher boiling points than NH3. So let's look at another importance of hydrogen bonding. And another one is in enthalpy of vaporization. The enthalpy of vaporization is the energy required to vaporize 1 mole of a liquid. The question we likely going to have here is, why is it that water has the largest enthalpy of vaporization when compared to the hydrides of the other group 6 elements like H2S, H2SE, and H2TE? Now, the key explanation here is that in water, for instance, there are intermolecular hydrogen bonds between the molecules. But in H2S, H2SC, and H2TE, they do not have intermolecular hydrogen bond. They have dipole-dipole interactions. And then when it comes to comparing strength of bonds now, the intermolecular hydrogen bond is greater than dipole-dipole attraction. Therefore, more energy will be required to break the hydrogen bonds. As a result of that, H2O has the largest enthalpy of vaporization. Take note of that. Then another one is in this application or importance of hydrogen bond will be to explain the boiling point and solubility of alcohols. So when we talk about alcohols now, we are talking about the alkanols, from methanol to ethanol to propanol to butanol to pentanol to hexanol to heptanol to octanol, nonanol, and decanol, and so on. Now, you observe generally that the boiling points of alcohols are generally higher than thiols. Uh, this is because the intermolecular hydrogen bonds exist in alcohols, while in thiols, dipole-dipole interactions occur. And like we have said, that in terms of strength, the intermolecular hydrogen bond is greater than that of a dipole-dipole interaction. So more energy will be required to break that intermolecular hydrogen bond. So that is the reason why the boiling point of alcohol is greater than that of thiols. Of course, when we look at the solubility, alcohols of lower molecular masses will of course be soluble in water because they can form intermolecular hydrogen bonds with water molecules. So let's look at another importance, that is in dimerization of carboxylic acid. Dimerization usually occur when carboxylic acid are dissolved in non-polar solvent or they are in vapor state. An example is when ethanoic acid molecule form dimers through the formation of intermolecular hydrogen bonds. So let's look at another application or importance. Another importance is in ice and water. There is an intermolecular hydrogen bond that exists in both ice and water. In water, for instance, the intermolecular hydrogen bonds are formed and broken continuously because water is always in constant motion, exactly a translational motion. So the arrangement will be random in that case. But in ice, for instance, the molecular motion is a bit restricted, and of course, the molecules will now be arranged in such a way that they can have maximum number of hydrogen bonds. Okay, so let's look at um, another one of the importance. Another importance there will be in proteins. We all know that the building blocks of protein is amino acid, and of course, amino acid have a hydrogen atom that is directly linked to an alkyl group, the amine group, and of course the carboxylic acid group. So, uh, if you look at how proteins are formed generally, uh, there is a condensation of this of this structure, and then they produce what is called a peptide bond. Now, when you have two amino acids combining together, they form a dipeptide. And these dipeptides are usually linked together by what is called a peptide bond. And in peptide bond, you have nitrogen directly linked with what? Hydrogen. So there is an hydrogen bond present in a peptide bond. So as a result, hydrogen bond helps in the formation of protein, like we have established the other time. Now, hydrogen bond is also present in the DNA. Hydrogen bond is present in the DNA, which contains genetic information. Okay, so let's leave hydrogen bonding and start look at van der Waals forces. Van der Waals forces is generally the sum of attractive or repulsive forces between molecules. Take note of that. Sum of attractive forces or repulsive forces that is between molecules. So the main focus here under van der Waals is molecules. And when we talk about molecules now, we can begin to look at hydrogen molecule, chlorine molecule, fluorine molecule, oxygen molecule, nitrogen molecule, carbon 4 oxide, CO, etc. These are molecules. So the van der Waals forces are named after Johannes Derek van der Waals. Okay, so let's look at the main characteristics of the van der Waals forces. They are weaker than the normal covalent and than ionic bonds. They are addictive and cannot be saturated. They have no directional characteristics. They are short-range forces, and they are independent of temperature except the dipole-dipole interactions. Okay, so they also have their own application in protein folding. They usually play a very great role in terms of stabilizing protein structure. They help in stabilizing protein structure. The second one is they are found usually in graphenes or graphite molecules. Of course, we know that graphite has a slippery nature, and that's why they can be used in lubricating oil. And then the slippery nature of graphite are usually attributed to the weak forces or weaker forces between their molecules, which is attributed to the van der Waals forces. And of course, they are applicable or they have importance in polymer formation. For instance, most polymeric chain are cross-linked by van der Waals forces, and then of course they get stable in the process. And of course, again, let me also point out that van der Waals forces are responsible for liquefaction of gases. We are able to liquefy gases in terms of liquefied gas, the fire extinguisher, the cooking domestic gas that we find. Gases are being able to liquefy because of the presence of van der Waals forces. It's a weak force, and of course, it helps quickly to liquefy gases. So it is also important. Van der Waals forces are used by some animals like wall geckos to climb, by some sea animals to move on water. And then of course it also have its application in modern technology. Okay, so let's also try and see how we can again be comparing the melting and boiling points of group group 6 hydrides, water, H2S, H2SC, and H2TE. So you observe that from this graph, you observe that water has the highest melting and boiling point, and it's as if the melting and boiling point, the melting and boiling point decreases as you are moving down. Why is this so? Um, the attractive force between molecules of water are stronger than that of the attractive force between the molecules of H2S. In H2O, for instance, you have the London dispersion force present, the dipole-dipole attractions present, and hydrogen bond is also present. So, but in the others, especially the H2O that we're looking at, it does have London dispersion force and dipole-dipole. So, because the attractive force in molecules of water are greater, then stronger forces will be required to break the H2O. So that is why H2O will have higher melting and boiling points than that of H2S and other ones respectively. Okay, so we can also look at the halogens, for instance. We observe that as you move down the group from top to bottom, the melting and boiling point will increase. The melting and boiling point will increase. From the graph you can see um, this is because there is greater interatomic attractive force between those atoms as you move down the group. So that is why they are like that. Now let's look at the other ones as well, those of the noble gas. The same thing will occur in noble gases. Why? Because um, the van der Waals force present in the noble gas will increase as you move down the group. So therefore, as you move down the group, the melting and boiling point will also increase. The same occurs with alkanes. Observe that the melting and boiling for the first 10 member of the alkane family, the melting and boiling point is also increasing. The melting and boiling point also increases. Of course, the you must know that the strength of van der Waals force in alkane molecules depends on the size of the alkane molecules. Longer chain, longer carbon chain alkanes, they will have large surface area and can form more than one contact points. So therefore, the longer the carbon chain, the more the van der Waals interaction and the greater the melting and boiling point. And that is why melting and boiling point is increasing down the group of the alkane family. Because as you move down the group, the carbon chain gets longer, and of course there will be increase in the surface area and contact points. So with that, we can now compare the bonds together. We can compare the bonds together in terms of the atoms that are involved. Let's quickly look at ionic, covalent, and simple metallic bonds. Simple covalent and metallic bonds. Ionic bonds usually occur with metals and non-metals. Covalent bonds occurs with non-metals only. Metallic bonds occur with metals. Ionic bonds form giant lattices that are brittle and can be broken easily or crushed easily. Covalent bonds usually form molecules with weak forces of attraction. Metallic bonds will form strong crystal lattice. An example of an ionic bonding is in bonding between Na and Cl. For simple covalent bond, that's the bonding between water molecules, and then for that of metallic, bonding between atoms of metals like sodium, aluminum, etc. Then ionic bonds usually have high melting and boiling points. Simple covalent, you have low melting and boiling points. The metallic also have high melting and boiling points. Ionic compounds are non-magnetic. Covalent are also non-magnetic, but metallic compounds are usually magnetic, at least some of them. So in terms of solubility, ionic bonds, most of them are soluble in water, or ionic compounds, most of them are soluble in water. Simple covalent compounds are not soluble in water. They are rather soluble. In organic solvent, while metallic compounds are not soluble in water. Well, metallic bonds rather. In terms of electricity now, in terms of electricity, ionic compounds can conduct electricity due to mobile ions. Covalent compounds cannot conduct. Metallic compounds can conduct when in solid or in molten form. Then an example of ionic compounds would be sodium chloride, used as flavor in food. Water is an example of simple covalent compound that is needed for life. Then copper is an example of metallic compound or metallic atom that is used for electrical wires. So let's look at some questions together. And one of them is why 2015. He says that the van der Waals forces are dominant intermolecular forces in. The answer is chlorine B. Like we have said, is the van der Waals forces is attractive or repulsive forces in molecules. And we have said that an example there is chlorine molecule. So van der Waals forces are present in chlorine more, or are dominant in chlorine more. Okay, so let's look at 2014. Hydrogen bonds are formed between molecules containing a hydrogen atom that is bonded to, the answer is A, strongly electronegative atom. Strongly electronegative atom. Hydrogen bonds are formed between hydrogen atom and strongly electronegative atom. And then of course, we look at this question again. We have to compare these two, SHN and OHN. Which one have a stronger hydrogen bond? It will be OHN. The simple analogy is that O is present in the HN there, while for the second one, while for the first one, S is present there. So, and between O and S, O is more electronegative. And like we have said, the more the electronegativity of that atom, the greater the strength of the hydrogen bond there. So OHN will be the correct answer here. So so far in the class, we have looked at hydrogen bonding. We've looked at hydrogen bonding, how hydrogen bonds are formed, and then we have looked at the types of hydrogen bonding, the intermolecular, intramolecular. We have looked at how some of the applications of hydrogen bonding in terms of anomalous behavior of some compounds like water, HF, in terms of their melting and boiling points, how it's applicable in forming stabilizing protein structure in DNA, and so on. And then we have also looked at the van der Waals forces and its own application as well. And then of course we have compared melting and boiling points of alkanes, noble gases, and halogens. based on the strength of the van der Waals forces that are present in them. So do well to take other questions and study again until you are able to take in everything. Continue to learn chemistry, and bye bye for now.